Let's have the usual table, horizontal. Object B. Object A. Remember, when we analyze Atwood system with Newton, we were usually concerned about forces or acceleration. As I mentioned earlier, now we're going to be dealing and be concerned about velocity. So let's imagine that we start from rest, and that object B is going to move by a distance d towards the right, and obviously object A is going to move by the same distance d down. And we will assume that the string doesn't stretch, and we will still neglect the mass of the pulley. But we're still going to consider friction on the table. Okay? So obviously, object A is going to go by a new distance, d, and object B is going to move by the exact same distance, d. And the question is, what is the velocity after that distance d? To make it easier, we're going to start from rest. Okay? So remember, Atwood, acceleration means Newton. Velocity means energy. Again, if you really don't like energy, you could always go back to Newton, figure out the acceleration, and then use kinematics to deduce the velocity. Or you can just use energy directly. So in this particular case, the first step is identify our system. In this case, we have two massive systems, MA and MB. So this tells us for sure, okay, as we write the energy conservation law, we're going to have a work term, then we're going to have the sum of all the kinetic energy for A and B, plus the sum of all the potential energy for A and for B at two states. What are the states? Obviously, let's pick one state when we start. And another state where we're interested of the velocity. So each object has two different states. And I'm overlapping 1 and 2 above B so that we can see it a little bit clearly. Okay, so I have my diagram. I have identified my two steps. Next one is to pick a current system, because we know we're going to need it for PEG. We have the choice to either pick one current system for both, or you could pick one current system for each. I will do the second case. I will pick one for B, and I will pick one for A. I would strongly suggest that you redo this problem by picking one that is common and see what the difference will be. As you will try that, you will realize that you're going to have to consider and insert a new variable that represents the initial position of object A with respect to B. But you will also realize that this new factor or variable will show up on both sides of the equation and will cancel out. So it will not matter. Okay, so point B, I'm going to pick my current system centered at position 1. Y up as usual, X centered here. And again, I'm putting it on top, but really should be here. It's just so it's a little bit clearer. Similarly, I will put my datum for A at the same position 1. Okay, so one current system for each. So every time I'm going to look at the potential energy term due to gravity for object A, I'm going to measure it from the x-axis of the current system of A. And then as I'm going to investigate the PEG for object B, I'm going to do it with respect to its own x-axis. Okay? All right. So next, work term. Do a quick free body diagram on object B and another one on object A. What are the forces acting on both? We've done this previous chapter. Go for it. Let's start with the easy one. Object A. What are the forces acting on A as they move from position 1 to position 2? Yeah. The weight, MAG, and the tension. Perfect. What about point B or object B? Excellent. We have the weight, mBg. We have the normal force, the tension, and the friction. Same as before. All right. So we have 6 different forces acting on different objects. Each of them will do work. But we know that the work done by the weight, we can neglect it. It's not 0, but we can neglect it because we're going to include the PEG for each. We know again that the normal force, the work done by the normal force doesn't have to be considered because as object B moves from 1 to 2, the normal force is perpendicular to the displacement dr. Therefore, the dot product will give us 0 and the work done is 0. We know how to calculate the work done due to friction, no problem. But we need to calculate also the work done by those 2 tensions. Let's calculate first the one we know, the work done by friction. Obviously, it's Fk again because object B is moving, as we did it many times. So we're going to end up with Fk dot dr between 0 and the distance d, which is also known. We know, again, dr is towards the right, Fk is towards the left, therefore pick up a negative sign. This is mu kn. And as you do a quick Fibonacci diagram on your head, you know you're going to pick a coordinate system such that y is vertical, and you can express n in terms of mg, and without involving neither t, neither fk, and neither a. Therefore, this will become mgd. Good. And this m is mb. Does everybody agrees with the functional form of the work done due to friction? Before I address John's question. All right. Excellent question, John. Nope, we wouldn't have, because then the tension will be considered as an internal force. Excellent question. So this suggests something. If you just said that, well, if we consider A and B as one system, and for some weird way we managed to get the right answer. Yeah, excellent, Honoka. And that implies that the tension, the work done by the tension acting on B, somehow is going to cancel out the work done of the tension acting on A. Let's see how that comes out. Excellent. Oh, you folks are on it. So let's calculate the work done due to the tension acting on B. And this, I'm only going to do it once, and I'm going to redo it as we move to chapter 10 and 11, as we're going to complicate the situation and include the mass of the pulley. And we're going to work out together and realize that it all cancels out, which means that it is not something that you will have to do on a test. I will assume that you know how to do it and you don't have to redo the math for me. Okay? But I want to do it at least once so that we all see it. So, by definition, this is going to be from 0 to d, tb dot dr. And I'm going to write tb to remind ourselves that it's the tension acting on b. What is the relationship between vector t acting on b and dr? That is, how are we going to do the dot product? Look at your free body diagram, plot dr. dr for B is towards the right, and dr for A is down. Let's do B. What is the relationship between vector t acting on B and dr? Yeah, they're both going in the same direction, towards the right. Therefore, the dot product is just a product of those two. Therefore, this becomes 0d tb dr. Bang. Now we can integrate. tb is a constant. The magnitude doesn't change if we consider a massless pulley. Therefore, we can take it out of the integral, and this becomes tbd. Okay? Since we assume that the pulley is massless, we are not given any mass, we used to call this t. So therefore, it's positive T times D. That's how much work this tension does acting on B. Let's identify the work done by the tension acting on A. Let's follow the same recipe. 0 to D. This time is vector TA dot dr. Now look at your free body diagram. What is the relationship between the vector, this should be A, vector T acting on A, and the displacement dr of object A? Yeah, opposite direction this time. Hence, since the angle is 180, we are going to pick up a negative sign, same as friction. So this becomes 0d TA dr. Again, TA is a constant, we can take it out, and this becomes TAD. And again, due to Newton's third law and the property of the pulley, this is what we used to call T. So this is negative TD. Hee-hee. That's the reason why we don't have to worry about it. So really, out of those 6 forces, which initially implies, holy crap, we need to have 6 work terms, really, we only have 1. 2 don't have to be included because we're going to include the PE. 1 does 0 work, and the 2 other are going to cancel out. And they will still cancel out each other as we consider massive pulley later on in chapter 10 and 11. It's a beauty. Perfect. So let's write down our energy conservation law with all the terms. First, the only work term that survives is the one due to friction, so we're going to have negative mu k mBg times d. Then kinetic, we have 2 massive terms, A and B. Later on, we're going to include the pulley as well. Therefore, we're going to have 3 terms. But for now, we only consider the system that have mass, therefore only A and B. Therefore, we need a kinetic term for A and a kinetic term for B. So, 1/2 ma VA squared plus 1/2 mb VB squared. The subscripts are going to become very, very, very important. And next chapter, we're going to add 2 or 3 subscripts. Potential. We have no spring, so we're going to concentrate on MGH or the one due to gravity. Okay, now let's duplicate all those 4 terms. And the first guys are for position 1. 1, 1, 1, 1, and all the other guys are for state 2. Okay, so each subscript is telling us a story. This is an example where you want to write your mathematics very, very clearly. It will help you. Now let's go through each term. Is the object A moving while it is at state 1? Excellent. No. Therefore, 0. Is object B moving as it is positioned at state 1? No again. Good. Is object B located on its own x-axis at state 1? Yes. Therefore, is object B located on its own axis at state 1? Excellent. So as you can see, at first we're like, oh, we're going to double the number of terms. At the end of the day, not too many survive. So it's good. All right. Let me duplicate. Oh, yeah, let me duplicate my diagram. Whoa. Right here. So we have B, we have B, we have A, and we have A. That's position 1, 2, 1, and 2. Okay. Next one Is our object moving? Is our object A? Ooh, why is HB? Excellent question. Because remember, I moved this above just so it was clear. That's why I redid it here. The question is our object B located on its x-axis at state 1? We decided to have a coordinate system for B, another one for A. Since we decided to put the original coordinate system at B as state 1, then B is located on the x-axis as state 1. Again, I did it above just so that it was a bit clearer, so that's why I redid it here, centered on the surface of the table. Does that answer your question, Ray? So we have positioned the x-axis of the coordinate system of object B right at the center of mass, right on the surface of the table. Perfect. Perfect, perfect. That's why in energy, please do a big diagram. So it's very clear for you and it's very clear for me, but especially for you. Because where you're going to put your x-axis is going to dictate all your PEG. So make sure that you make a big, clear diagram with both your position 1 and 2 or A and B for each of your system. Good. Now, is my object A moving while it is at position 2? Yep, it is. Therefore, we keep it. Is my object B moving while it is at position 2? Yep. Plus, we know that the string doesn't stretch. Therefore, we know that the magnitude of those two velocities, VA and VB, are the same. Hence, feel free to drop the subscript. And that's what we're looking for. So you can only keep the subscript 2 to remind you that the velocity has state 2, or you can just drop it all like we did before. You decide. All right. Now, next question. What about this guy? Is object A located on its own x-axis while it is in state 2? No, it's below. State 2 is right here, and its x is right here. Perfect. So we know it's not going to be 0. We have to keep it, and we know it's going to be negative. By how much? Or what is HA2? What is the vertical position of? Excellent. Therefore, this is negative MA G D. And again, keep track of who's A, who's B, like usual. Good. Next one. Is object B at state 2 located on its own x-axis? Yeah, it still is, because the table is horizontal. Yeehaw! Done. So really, out of those 1, 2, 3, 4, 5, 6, 7, 8, 9 remaining term, we really have only 3 or 4. Piece of cake. That's it. Now we can solve for V. So as you solve for V, you're going to move this term on the other side. So you can factor G out. So we have GD. We have MA minus mu K MB. And then we have a factor of 2 coming from an n the square root. And then we're going to divide by, am I forgetting something here? Yeah, by the total inertia.